Last time, Zeno left us with a wound in reason. Motion was real, yet every frozen instant appeared still. At the edge of that paradox, one idea began to emerge, a limit. But the story was not finished, because now an even bolder question appeared. If infinity can be approached, can it be measured? Centuries before Newton, centuries before the symbols of modern calculus, a mind from Syracuse stepped into this question with extraordinary confidence. His name was Archimedes. Zeno had made infinity feel like a trap. Archimedes would begin turning it into an instrument of proof. Begin with a circle. It is perfect, simple, and deeply inconvenient. Its edge is curved everywhere. A polygon can be measured. A circle refuses to become straight. So Archimedes did not attempt to seize the curve at once. He surrounded it with what geometry could understand. Place a hexagon inside the circle and another around it. Now double the sides, 12, 24, 48, 96. Watch what happens. The inner boundary rises toward the circle. The outer boundary descends toward it. The uncertainty is being squeezed from both sides. At 96 sides, this was no longer a rough picture. It became a rigorous trap. Archimedes showed that pi is greater than 223 over 71 and smaller than 22 over 7. The curve could not escape the bounds of geometry. This is the method of exhaustion. Approximate, refine. Reduce the remaining error until the only possible truth is forced into view. Zeno divided forever and found danger. Archimedes refined forever and found measurement. Then he chose an even more astonishing target, a region enclosed by a parabola and a straight chord, a curved area. No ordinary triangle can fill it completely, but Archimedes saw that the unfilled gaps were not disorder. They were a repeating pattern. Start with one large triangle. It captures most of the parabolic segment. In the gaps, place two smaller triangles. In the new gaps, place 4 more, then 8. Each generation is smaller, but together they add a precise fraction of what came before. The first triangle has area t. The next generation adds 1/4 of t, then 1/16, then 1/64. An infinitely complicated curved region has become a disciplined sum. T plus t over 4 plus t over 16, continuing without end. And the pattern converges. 1 plus 1/4 plus 1/16 plus 1/64 approaches 4/3. Therefore, the parabolic segment has area 4/3 of the first triangle. Infinity has not destroyed measurement. Infinity has completed it. Archimedes did not have the integral sign. He did not have coordinates, derivatives, or a modern theory of limits. But the heartbeat of integration was already here. Break a curved whole into refinable pieces, sum their contributions, and control what remains. His geometry reached into 3 dimensions. Imagine a sphere perfectly enclosed by a cylinder. Curvature now exists in every direction. Yet Archimedes discovered that the sphere has 2/3 the volume of the cylinder around it. A curved solid had yielded to exact comparison. A circle, a parabolic segment, a sphere. These were not isolated miracles. Together, they revealed a new intellectual power, accumulation. Geometry could approach the infinite, sum the vanishing pieces, and arrive at truth. Archimedes had shown that infinity could be approached with discipline. But his triumph also opened a new question. Geometry could measure shapes. What about a world that changes from moment to moment? A falling stone, a moving planet, a speed that refuses to remain constant. Zeno made infinity a paradox. Archimedes made infinity a method. The next chapter begins exactly where his geometry leaves us, not with another name, but with a new problem. How can mathematics measure a world in motion?